Okay, so in this example, we're going to look at conservation of momentum in 2D. This is a person who will be walking across a raft that's going down a river. So we have a person, mass of 50 kilograms, standing on a floating raft with a mass of 120 kilograms. The raft is going down the river at 1 meter per second east. Then you start walking at 0.600 meters per second north. We want to find the velocity of the raft after you start walking. So in this diagram, we're going to look at a bird's eye view. So this is the raft. This is a bird's eye view of the person standing on the raft, and the water is going downstream at 1 meter per second. So if you are standing on a raft, stationary, total momentum of the system is going to be the mass of the person plus the mass of the raft times the velocity of the water, which means the total momentum is the 50 kilograms of the person plus the 120 kilograms of the raft times the velocity of the water, 1 meter per second east, which gives us a total momentum of 170 kilogram meters per second east. So momentum has to be conserved in interactions. So this is what we started with. This is what we will end with. So now if you start walking across the raft, you're going to be walking at 0.6 meters per second north. The raft is actually going to start moving in the opposite direction due to Newton's third law, and everything is still floating downstream at 1 meter per second east. So total momentum before the interaction has to equal the total momentum after. Total momentum after is a combination of the mass of the person times the velocity of the person plus the mass of the raft times the velocity of the raft, but we don't actually know what this is going to be. So we had total momentum before was 170 kilogram meters per second east. Here is the person walking at 0.6 meters per second north. I'm just going to leave the raft part here because we don't know anything about the velocity. So 170 kilogram meters per second east minus 30 kilogram meters per second north is equal to essentially the momentum of the raft. Let's draw it out just to see what that vector diagram looks like. So this was the momentum before, 170 kilogram meters per second east. Now, minus 30 kilogram meters per second north. So it looks like this. So 170 kilogram meters per second east, negative 30 kilogram meters per second north. We notice we have a right angle triangle. We can solve for the hypotenuse. And when we solve for it, we get 172.6 kilogram meters per second. The angle, which is theta right here, is just by using tan. It's 10 degrees. And we know that the momentum of the raft is equal to its mass times its velocity. We have its momentum here. So 172.6 kilogram meters per second. Put the direction right here, which is east 10 degrees south, divided by the mass of the raft, gives us a velocity of 1.44 meters per second, and the direction would be east 10 degrees south, which essentially means that when you get on the raft and you start to walk, the raft is going to actually be moving not just downstream, but towards the shore.